Talking about binomial trials. A binomial trial is an experiment with only two outcomes. So the quintessential binomial trial is heads or tails on a coin. And we discount the possibility that the coin lands on its edge. Okay, for a drug or a treatment, we would say the drug or a treatment is effective or ineffective. And that would be a binomial trial. Or if we were manufacturing something, we could say that the item is defective or working. Okay, those are the possibilities we'd get when we're manufacturing something. And in general, we use the words success or failure when we talk about a general binomial trial. We talk about success or failure. Okay, so when we have a binomial trial, P, the letter P, lowercase up, will stand for the probability of success. And then Q, which is then 1 minus P, because there's only two possible outcomes, this is the probability of failure. Now, just one binomial trial is not very interesting, right? With probability 1/3, something happens. With probability 2/3, that thing doesn't happen. That's not the interesting thing. The interesting thing is you're going to repeat this trial n times, some large number of times. And we assume each outcome is independent of all others. Okay. So, like flipping a coin 5 times, what we got on the first 5 times shouldn't have any bearing on the 6th time, if the coin is fair, right? Okay. So, in a moment, there's going to be a really nice formula that just tells you exactly what's going on here. So that's the good news, that there's a nice formula. The bad news is it involves combinations, right? But we learned about those. So one more bit of notation that we haven't seen before. We've used taking n things and choosing k of them, where order doesn't matter, to be C, N, K, the combination of N, K. The book is now going to switch notation for these and write this as a parentheses with an n on top of a k. Now there's no fraction bar in between. It's just an n over a k. It's a 2-line formula. And this is read n choose k. So instead of combination nk, we're going to say n choose k. This is just the common way of referring to this. So now I'm going to write down the formula that tells you exactly how to figure this out, and then we'll do several examples to see how it works. Okay, so this is the binomial probability formula. Okay. If the random variable x is the number of successes of a binomial experiment with n independent trials, with probability of success P, and Q being 1 minus the probability of success, then the probability that you have exactly k successes. So you do the experiment n times and you're looking for k successes. It's n choose k times p to the k times q to the n minus k. So n choose k times p to the k times q to the n minus k. Another way of writing this, in case you forgot the combination formula, n factorial divided by k factorial, n minus k factorial, p to the k, q to the n minus k, like that. So this is much quicker than other methods we might have of counting things, right? Like if we were going to say, I want to flip a coin 5 times and say, what's the probability of getting 3 heads? Well, 5, we can write that down, right? We can write down the 2 to the 5th possible outcomes that we would possibly get and count how many of them have 3 or more heads. Right? We could do that. It would not take that long. But if instead of 5 times we said 500 times, now we're in trouble, right? We can't write down all the possibilities and count them up. And so this formula allows us to do something like that very quickly. So let's do a simple example with this formula. What is the probability that a coin tossed 10 times will get 3 heads? We're going to toss a coin 10 times and say how often or how likely is it that we'll get exactly 3 heads. So in the language of the formula, this is the probability that x is equal to 3, where x is the total number of heads that we get, the successes. So using this formula, it's 10 choose 3 times the probability of getting a heads cubed times the probability of getting a tails to the 7th power, which is 10 minus 3. So that's what happens when we plug into that formula. 10 choose 3 turns out to be 120. And this altogether, because the probability of success and failure are the same, this is just 2 to the 10th in the denominator there, and 2 to the 10th is 1024. And when we multiply these two things, this is about 0.12. So there's a 12% chance you'll get exactly 3 heads. Not very large, but definitely possible. Right? If you do this 10 times, you'd expect it to happen once, perhaps. Right? So it's not entirely rare. So this is much quicker than writing down all possible combinations of 10 coin tosses, right? This is a good deal better than that. Very quick. Okay, so here's another example. We'll do a few more examples with our time today. So a company produces plastic washers packaged in boxes of 300. Okay, so you buy a box, it's got 300 plastic washers in it, but there is a 2% defective rate. 2 out of every 100 about are defective. And the question is, what is the probability that the box has exactly 9 defective washers? So now we're looking at the probability of 9 successes. Now we'll define success here to be is a defective washer, which is a strange definition of success, but it'll allow us to just apply the formula simply. So we have 300 trials, and we're looking at 9 successes. The probability of success is 2%, and then the probability of failure, the failure of being a perfectly good washer, is 291, or is 0.98, and then we raise that to the 291st power. Okay. So if you haven't gotten a scientific calculator to use on tests so far that has combinations in it and things like that, it's probably a good idea to scare one up somehow, right? You can probably steal one from a roommate or something like that, right? Right? You go to a party at someone's dorm room, right? Like they go to the bathroom, you grab their scientific calculator, then you got it, right? I mean, or you could spend like $10 or $15 if you want to do the more honest thing. But having the combinations or permutations right there in your calculator would be very helpful. Okay, so we actually do this, blah, blah, blah. Magically, someone has a calculator, and we get 0.07 for the probability here. So it's a 7% chance that we'll have exactly 9 defective washers. Now, of course, most of the time you don't care about exactly 9. You want to know, well, what's the probability that I have less than 9 defective washers, right? Well, that's a little harder, right? Because that's the probability of x is less than or equal to 9. And so to do that, you would have to do this calculation 9 or 10 times. One for 0 defective washers, one for 1 defective washer, all the way to the probability of there being 9 defective washers, right? So you'd have to do that formula 10 times, which is that's kind of a pain in the butt, right? That would be a long problem. But it's doable, right? I mean, before today you had no way of doing that, right? So even though this would be a chore, at least it's a chore that can be done. You could actually find this out. Whereas before we learned this formula, we would have been kind of like, I don't know, 20%, like we just sort of guessed something, right? Like we'd have no way of figuring that out. Okay, here's another example here. So let's say a hitter, this is a baseball example. A hitter has an on-base percentage of 451. If he comes to the plate 5 times in a game, what is the probability he reaches base? So we are going to view each plate appearance that the batter makes as a binomial trial that has a 0.451 probability of success and then a 0.549 probability of failure. So the actual answer to this problem then is going to be the probability that we have 1 success plus the probability that we have 2 successes plus the probability that we have 3 successes, the probability that we have 4 successes, and the probability that we have 5 successes, right? This would be reaching base once, and this would be reaching base all times. Okay. So we could calculate those 5 separately, right? Except there's an easier way to do this, right? The probability that he reaches base at least once is 1 minus the probability he does not reach base. And that time we'd only have to do 1 calculation. This should be the same as 1 minus the probability that the batter does not reach base. And that one, we'd only have to use our formula 1 time in order to do this calculation. So this is 1 minus, okay, 5, choose 0, times 0.451 to the 0 power, times 0.549 to the 5th power. Okay, and I've got a mistake on my page here, so I better calculate this. Okay, so this is 0.549, and then I need like a fancier calculator. No. This is the best you can give me, calculator? Ah, there we go. Okay. To the 5th power. Okay. So this is going to be 1 minus... How many ways can we choose 0 things from 5? That's 1. 0.451 to the 0th power is 1. This is 0.549. So this... No, this is this is 0.04987. So 1 minus this is about 0.95. So there's a 95% chance that this person reaches base at least once in the game. That's pretty high. Okay. Questions about that one? Okay, let me give you a tip for using a TI calculator. This is in the textbook, and if you have one of those calculators and you know, in the time remaining here, you want me to help you find out how to do this, I'd be happy to do that. Apparently, it's in the second you press second, and then you press distribution, and then maybe it's in menu B. And the command is BNOMPDF. So that's binomial probability distribution function. And there's 3 arguments that you put in here. This is number of trials. This is probability of success. And X is number of successes. So as far as our book is concerned, X is the K that we've been talking about. Okay? So if you want help with that, I'd be happy to help you in the time we have remaining. Let me write down the homework assignment for Monday. 18, 20, 22, 28, 34, 42, 44, and 52. All right, folks. We got a few minutes. If you want some help with that calculator thing, if you want to start looking at this, that's great. Otherwise, have a good week.